I guess we're gonna just today, the only thing we will be doing, short Friday, we'll be going over the answers to the centripetal force circular motion study guide assigned yesterday. So let's take care of some review questions from earlier in the week, or from even past units. The net force acting upon an object is A, in the same direction as the object's acceleration. The overall net, remember net means total, is always in the same direction as the object and the object's acceleration. So if there's only one, basically how that applies to this stuff, if there's only one force involved in making something go in a circle or affecting it, that one force is the net force, and it points towards the center too. Therefore, since its acceleration is called centripetal, which means towards the center, in this case, the force is centripetal, which just means points towards the center. So in number 2, it says, consider the top view of a clockwise motion of an object shown at the right. So this object's going in a circle like this. Draw an arrow to indicate the direction of these three things. The acceleration, right? The acceleration should point inward at location A, at all locations, but this is specifically location A. And B, the velocity vector at location C, and the velocity vector at location D. Remember, those point tangent or a straight line off the circle. And although it looks like it didn't ask, the force vectors, I don't know if it was supposed to ask and it's not there, but the force vectors you can see are drawn on positions E and B, and they point inward as well. The main thing here is that the force and acceleration vectors would point inward. The velocity points tangent to the circular path. Okay, so yesterday we described some things in the notes and in yesterday's video, or in class if you were in class, about the term centripetal force is a kind of a generic term. If I asked you what force is making something go in a circle, it's a generic answer to say a centripetal force. Yes, it does take a centripetal force to make something go in a circle, but you could think of centripetal force as just a category of specific forces that are making something go in a circle. All right? And I listed yesterday the most common specific forces we've already learned about in the past that could be centripetal, or in other words, could make something go in a circle or partial circle. And those were tension, normal force, gravity, or frictional force. I'm not saying there's not other forces that can make something curve, but those are the most typical ones. Okay? So we just have to specifically list from the situation which one of those sounds like in the situation would be the centripetal force. So anytime an orbit happens, it's gravity. So a planet orbits the sun, answer gravity. A bucket is filled with water held by a string. Anytime there's a string, rope, chain, cable, something like that involved, the answer is going to be tension, is making it go in a circle. Letter C, passengers on the cliffhanger amusement park ride, a barrel ride, are rotated rapidly in a circle. There's a lot of variations of amusement park rides where you are in a cylinder, would probably be better to say than a barrel, but that could get a barrel as a cylinder anyway. Many of you living around here might recall the ride at Idlewild called the Roundup, which is you go in a cylinder basically with your back against the wall, it spins and lifts you up. And there's a lot of variations at different amusement parks of that kind of ride. Okay? But the main thing, your back's against the wall and it gets you spinning fast, and because you want to fly off, the wall has to push back on you. And we learned in the past, a surface pushing back on something is a normal force. So in any kind of ride like this or any variation of it, the centripetal force is supplied by the wall behind you, pushing back on you, which is a normal force. All right. D, there's orbiting it. I don't care what is orbiting. If it says orbiting, the answer is gravity. A car is making a turn on a level roadway. We went over this situation yesterday. A car rounding a turn, that's friction. All right. But another thing I noted yesterday is that sometimes multiple forces can help you stay on a turn, like in a vehicle especially. This is why we bank turns in civil engineering to make them more easily to stay on, that you don't fly off. If a road is flat or level, only friction, like in Part E, is helping you. But if it is banked, then both friction and normal force both help you around the turn. More force is helping you is better to stay on the turn, right? So anywhere there's turns on roads that have higher speed limits, you're going to have bank turns which uses normal and frictional force together. All right, in football, a halfback, just a running back, leans in and rounds a corner to head upfield. Rounding a corner on a flat surface, remember, like a car, it's friction. But same with a person. Your feet are just your tires, and if you're on a flat surface, it's friction as well. Just friction, it's a flat surface. Roller coaster in a loop. The loop pushes back on the coaster, therefore normal force. But also, and I'm going to talk about this more next week, if it's at the top, gravity is interacting with you as well. The main one's normal force, though. If you're at the bottom of the track, it's not that gravity's not there, but it's totally just normal force helping you around the track. Right there. Clothes move in a circle in a spin cycle in a washing machine. This is normal force. This would just be like similar to the barrel ride one up here. Instead of a ride and people in a cylinder, clothes in a cylinder spinning is just normal force by the wall of the ride. And just a little extra FYI, the spin cycle partially dries the clothes so they're not sopping wet. How it happens is, if you ever looked into the cylinder of your washing machine, it's full of little holes. When it spins rapidly, remember, when things go in a circle, they want to fly off the circle. But typically there's something not letting them there. The clothes can't fly off the circle because the walls of the drum, the barrel, the cylinder in the washing machine, they just plaster up against it. If you open the lid after the spin cycle is done, all your clothes are like plastered against it because they wanted to fly off that whole time, and they stick against it. But what happens is the water in the clothing also wants to fly off. The holes allow it to fly off, partially drying them. If you didn't have a spin cycle, then the clothes would be sopping wet and take forever to dry, even in a dryer. All right, next couple questions are just certain positions and certain kinds of loops. Oh, number 4. Okay, this is where it came in. I just forgot. We already answered this one. It said in number 4, go back to question 2 and label the force vectors in E and B. So that's where it officially asked you to do that. Point the forces inward on those ones. Number 5, so here's a roller coaster loop. In a roller coaster loop, there's many positions, but the two main and most important positions are the top of the loop and the bottom of the loop. Both normal force and gravity are present at each position, but how they interact differently at each position. So it says two strategic positions on the loop are the top and bottom. In the diagrams below, draw force vectors on the riders to depict the direction and magnitude of these two forces acting on the riders. The size of the force should be approximately equal to the size of the vector arrow. Main thing is you get the forces and direction right. At the bottom of the loop, the track is underneath you, so the normal force is up, and gravity always pulls down on you no matter what. That can't change. All right, so it should look something like this. And technically, the normal force is greater at the bottom of the loop, and you're compared to the force of gravity, aka your weight. But at the top of the loop, well, again, gravity always points down, but now the track, you're underneath the track, and the track's pushing back on you, providing the normal force, so the normal force is also down at that position. So they interact differently at these two different positions. When the roller coaster car is at the bottom of the loop, the direction of the acceleration and the net force is directed. This is just describing what we just drew, really. But in terms of net force, remember net means total, right? So if at the bottom position, the normal force is greater than the force of gravity, you feel more pressure from the track at the bottom when it's a circular loop at the bottom. The net is just the total. So if the normal is bigger than the gravitational one, then we still have the overall net is upward. All right. When the roller coaster is at the top of the loop, both forces point down, so the net total has to point down as well. All right. And again, just kind of answering a similar question, just worded a different way. In order for the conditions described in number 6 above to be true, how does the magnitude of the normal force compare to the magnitude of the gravity force? How does it compare at the two locations? Put a greater than or less than symbols in the blanks below. Well, we already noted at the bottom, you actually at the bottom of the loop feel like heavier. That's because the normal force of the track pushing back than you is greater there. Okay? Now on the answer key, you could see they have a question mark here. And that makes this somewhat of a trick question. So if you got it wrong by guessing one of these two, you were kind of led to believe it should be. But actually, there's a question mark there because really it just depends. Okay? If you're going really fast through the loop at the top, then the normal force might be greater than the force of gravity. However, if you go so slow through the loop that you just barely make it through the loop, the answer could change. The gravity force could be greater than the normal force for a brief moment. And that would put you in, if you're going too slow, in danger of actually falling off the loop. Now, on a roller coaster, there's safety precautions engineered into it. So if something weird happened and you went too slow around the loop, if something for some reason weren't going as fast as you should, you wouldn't actually fall. Your cart has like wheels attached to the other side that kind of hook you onto it. But technically, if you're going fast enough and you could guarantee nothing could go wrong, which obviously we can't guarantee, but if you could, you wouldn't need any of those safety hooked wheels around the other side, because you would have plenty of inertia to make it through without worrying about falling off. So for that reason, that's why the key has question marks. It really depends at the top of the loop. It doesn't depend at the bottom. You don't need a minimum speed to get it through the bottom. It does at the top. So that's why that one could be either, depending on how fast you were going. All right, number 8. A person's sensation of weight is due to the presence of a normal force upon their body. We actually talked about that way long ago prior to circular motion. We just said that you won't feel like you weigh anything unless something pushes back on you. The reason why a bathroom scale works is because when you step on it, it pushes back on you, and there's either a digital sensor or a spring-loaded sensor for the needle in there to read the force pushing back on you. All right? And as it goes on to say, usually this normal force is the same magnitude of the force of gravity, as long as you step on a bathroom scale at rest. So a 600 Newton person typically feels 600 Newtons of normal force to provide a sensation of how much they weigh. When the normal force becomes greater than or less than the force of gravity, a person has a sensation or feeling heavy or feeling light. Where on the roller coaster loop would a person most likely feel heavy, top or bottom? And the answer is bottom. All right, it says explain your answer. When you pass through the bottom of the loop, one way to answer it is that your normal force and gravitational force, you can see from the diagram we made up here, are opposite of one another, kind of fighting one another, making you feel heavier. But it's also due to the acceleration that you have. We noted back with elevators, when you have a positive upward acceleration on you, let's just use upward instead of positive because we can decide whatever direction's positive or negative. When you have an upward acceleration on you in an elevator, you feel heavier if you had a bathroom scale underneath you. The same thing would occur at the bottom of a loop Because you're not on a flat surface, you have an upward centripetal acceleration on you. And similar to the elevator examples from the past, that would cause you to feel heavier since you have an upward acceleration. So saying anything along those lines would be the best explanation for your answer. Let's look at number 9. The centripetal force, this is true or false, is a distinctly separate force. It can be added to the list of forces along with these other ones that might act on an object, and that is false. That goes back to this question and what things we discussed about it yesterday. The centripetal force is just a general category of forces that can maybe make you go in a circle. So it's not its own unique, or I don't want to say unique, it's not its own specific force. It's a category of forces that make something go in a circle. And tension, friction, normal, gravity are examples of specific types. So that's why this is false. Although it didn't ask it, a question that is like number 8, I'm going to end today going over. At the top of the loop, you would actually feel lighter, not heavier. Where you said in number 8 at the bottom you feel heavier, you would feel almost like you come out of your seat, basically, if you weren't strapped in at the top of the loop, especially if you were going just fast enough to make it through. And that's because the centripetal accelerations are now downward here as compared to the bottom. If you were going the same speed at the bottom of the top, you would feel lighter at the top compared to at the bottom. Okay? But overall, I would say the most important things to remember about the study guide is that the force making you go in a circle is centripetal. It points along the center just like the acceleration, and know these specific common forces that could be centripetal or make you go through a circle. We've got some other little activities to do on circular motion next week, but probably before the end of next week, there will be likely have a quiz on these study guides, so make sure you keep them. Have a good weekend.